Good morning, everyone. I think we have our quorum for our morning session. Welcome back for our final day of the PETSc annual meeting. So between now and our morning coffee break, we have a session that is centered around plasma physics and related enabling technologies. So the first talk in this session is going to be Professor Chonglin Zhang from RPI, and he's going to talk to us about what he and his team have been doing with XGCm. So, Professor Zhang, can you say something to make sure you're unmuted again?
Hi, Toby. Thanks to clarify, I'm not yet a professor yet. I'm just Dr. Zhang.
Okay.
Thank you.
All right. Thanks again for joining us. The floor is yours.
All right. Thank you, Toby. Yeah. Good morning, everyone. Thanks for attending my presentation. Sorry, I was not able to join you guys in Chicago. So today I will be talking about our work developing XGCm, unstructured mesh.
Recording in progress.
Okay. Developing an unstructured mesh Gyrokinetic particle cell code for fusion plasma simulation. So this is the work with together with Dr. Gary Diamond, Cameron Smith, and Professor Mark Shephard. So at RPI. So first, okay. First, let's overview what is XGCm. XGCm is basically the new developed code for gyrokinetic particle cell simulation and for plasma fusion plasma simulation. So I would talk more about what is gyrokinetic. Does gyrokinetic mean? So basically, it's a mesh-centric approach to handle particle operation. We use a mesh-centric approach to handle all the particle operations and use distributed unstructured mesh. Like this is our with our very good technical expertise in these areas, and the physical algorithm is adapted from the well-established XGC code, which was widely used in the fusion plasma simulation community. Also, in terms of library, XGCm depends on several libraries. First is the Omega H library to interface with unstructured mesh for unstructured mesh management. So this is Kokkos-based library, and then the PUMIPic library, which used to map for particle management, and it's Omega H based. Finally, it's a PETSc for linear equation solver, so which can interface with both CPU and GPU. I'll discuss more later while we work on this one. So you already saw from Jin Chao's presentation yesterday, he discussed like a PETSc on CPU and also GPU solver. So for XGCm, all operations are performed on GPU currently. So currently we are working on NVIDIA GPU. We are porting to AMD and Intel GPU, so on the way. So objective of this XGCm is as a test bed for developing new algorithm, which can be eventually incorporated into XGC code, and also aim at the Exascale fusion plasma simulation. So here I'm just showing example simulation result. You can see the 3D simulation, like how there's basically particle moving inside the torus, like a tokamak device, and this line is just a particle trajectory. So how just overall what the simulation looks like, and you can see the mesh, each polar plane mesh, you can have different quantities. For example, here I'm showing the electrostatic potential. So that's just the overall overview of this XGCm code. So in terms of outline, today I'll discuss about what is particle in cell, gyrokinetic particle in cell method, and then discuss our different depending library like Omega H, PUMIPic, and the PETSc, and then we'll discuss a little bit code validation using a cyclone base case, and then the code performance and scaling studies. And the future work. So with this one, first, what is the governing equation is for the particle in cell method is governed by the Blavsov equation. So this one starting from the Boltzmann equation. Some may not know, it's basically the Boltzmann equation describe the particle velocity distribution function involvement in evolution over the physical space, 6D physical space as both function of space and the velocity. And you have a right-hand side of the collision term basically describe how the particle or the molecule or atoms, they charged species interact with each other during collision. So with long-range Coulomb interaction in the plasma physics, you can have basically the collisionless Boltzmann equation. You can basically, the right-hand side collision term will be 0. And then for plasma, you have the Lorentz force on charged particles based on its electric field and also the background magnetic field. Or this will give you the velocity equation. Basically, you can see here is plug in the acceleration term from this one, plug in the acceleration term into the Boltzmann equation. Also, since like when the charged particle moves, like they form a electric field. So this electric field this electric field then further determine how the particle actually move, how particle actually move. So that's what we call the self-consistent electric field. This is basically the Poisson equation you can see here because electric field is a function, is a gradient of the electrostatic potential. So basically the Poisson equation with the right-hand side. So this is the overall like how the overall like theoretical background is. And then in terms of particle in cell method, like basically numerical solve the velocity equation, and it is a Monte Carlo particle method. So in this method, like each particle represents a large amount of identical real charged ions or electrons. So there are 4 operations in a PETSc method. You can basically the first is if you refer to the velocity equation, you can see like first is a particle push corresponding the particle movement convection. Basically, you can due to the velocity and the external force, like this term, and then you have the self-consistent electric field that determine the particle charge deposition. So basically, this particle charge is supplied into your self-consistent electric field like Poisson equation, and then you field solve, basically solving this Poisson equation to get the electric field. And then from electric field, then you go back to the particles field particle interpolation. So interpolate the electric field back to the particle position and then repeat this process. So that's the overall like a PETSc method. With gyrokinetic particle in cell method, like here showing the particle trajectory in the tokamak. If you show here, this red curve is the particle actual trajectory. Because of very strong magnetic field in the tokamak, so particle follow this gyration motion. And instead of modeling the particle actual trajectory, we all usually just model the particles getting center position. Basically, is the black line here you see here showing here getting center position. So this is the main idea of the gyrokinetic particle in cell method. So with reduced, you did not like model the particle actual trajectory. So of course there is going to be a lot of theoretical details going to how you formulate this gyrokinetic particle PETSc method. So with this one, let's talk about the unstructured partition mesh omega h. So this omega h is what our mesh infrastructure used to interface with DPU device. So we have a 3-level mesh partition. Basically, you can same example shown here. Tokamak, like you see, first we have the toroidal partition. Basically, partition particle into different ampere racks along the torus direction. For example, you have different along different. So there's different correspond to different partition here, and then we have polar partition. Basically, this corresponds to a, you can see here with one polar plane, which we call the polar plane in the fusion plasma. So fusion like a plasma community. So within each polar plane, mesh is partitioned into different ampere ranks according to the flux curve. Basically, this is the flux curve. If you see this line like donut shaped or concentric circle, this one corresponds to one flux curve. So mesh is partitioned into different ampere ranks. So here, like for example, this corresponds to one partition, mesh partition, another mesh partition. So all these different colors, like the region is correspond to different partitions. So, and then we have a third partition called the solver partition. This is potentially we can have different mesh partition in each polar plane for solving basically Gyrokinetic Poisson equation. For example, here people doing use PETSc, you know, like you can have different, you can partition a mesh just this way with different compared to the polar partition. But like for example, here I've shown two different partitions like in this polar plane mesh. But as a first step, we use the same partition, like solver partition, the same as polar partition. So I'll discuss later why we do this one. So this is like our overall like mesh partition. And then let's talk about the particle management, because it's a particle in cell code. So we always have particles, and the particles interact with like a mesh. So our approach is we have a distributed mesh approach for particle in cell. So because where particles access through the mesh, so we have a mesh-centric approach to. So the idea is to be able to support this like a mesh-centric approach where our hope to support a faster data access and match particle operations, though because of better data locality. So this we'll discuss later in the performance section. So basically, like a mesh distribution, like is based on the core parts and the buffer part to ensure like unprocessed movement of particles in a particle push operation. So this is basically the mesh infrastructure to support all the major pick operations on the GPU. For example, particle mesh and the mesh operations. So basically, the PUMIPic is an infrastructure which is very light to which we can use to develop not only XGCm, maybe other particle simulation code. So here I'm showing a pick part generally for the core part A. For example, this part is A, and then that's their buffer region surrounding by the part A. And then in terms of like a particle movement and association with in this unstructured mesh, you can see here this is like you can think about this seem like a mesh, but it's in 2D. It's actually particle moving in 3D. But here I'm just using 2D as a demonstration. Particle trajectory movements through a 2D like triangle mesh using. So basically, what we do is we use edge adjacency to search particle from the initial position to its final position to do adjacency based search. So which is very time like efficient. In terms of particle like association with like a mesh, we have different mesh particle state structures. For example, here we're showing some like a mesh element, a triangle element. There are some particle inside it. On the memory, on GPU memory, for example, we can use CSR this structure, like CSR similar as what you have in a sparse matrix compressed sparse row like a matrix format. How to store particle inside your GPU memory. The main like a lot of big like different disk structure we use is called the cell C sigma disk structure. Basically like a cell C sigma disk structure. This is work by Dr. Diamond. So he based on the other people's work, he come up with this very nice data structure part called cell sigma disk structure to store the particle information onto the GPU memory, and this was to store. So we store on the GPU memory. So I will not go into the details since it's very involved. So now let's talk about how solving electrostatic Gyrokinetic Poisson equation using PETSc. So the equation being solved basically is you can see here you have the long nodes, basically electrostatic potential, and with some like a guiding center density. Basically the density, the right hand side is basically guiding center density, and basically this is you supply from the particle simulation, and then on on the left hand side, the matrix, linear matrix is basically this is the constant because in the tokamak usually in our case like we're not right now interested in the electrostatic simulation. So the electromagnetic field is constant. So basically the linear matrix is the constant. So in terms of solution process, like first after the particle push operation, like we can obtain the right-hand side vector, that basically the charge density resulting from the charge scatter, basically obtain the right-hand side vector, and then copy the right-hand side vector from omega h to PETSc and then solve either on CPU or GPU with PETSc. Because like I mentioned, the linear matrix is assembled once on GPU in the initial setup stage because the constant does not change. After that, after the PETSc solve, we copy the solution vector from PETSc to omega h like a mesh field. So, and then calculate the electric field from solution vector and perform another particle push. So then repeat the above process. So in terms of field, like basically right-hand side and solution vector. So the storage if we are solving on GPU, the data state on GPU memory based on using the omega h like omega h data structure, omega h read, or based on whether you're doing memory access is read or read only access. You have different like data structure, data types. And if you solve it on CPU, the data is copied to CPU memory from PETSc, and then you have a different omega h data type, like for example, omega h host, write, host, depending on whether you're doing data both reading or writing, or just only reading. So you have different data types. So just in case you change the data unwanted. So that's over like how we do the over like a solution process like interface with PETSc. And so before we solve we copy the right hand side vector to PETSc. So basically, depending on whether you are this very discuss some code you see here. If we're solving on GPU, we basically do the parallel fault, similar to what you have in Kokkos parallel fault, but the omega h parallel fault. So you just looping over all the mesh vertices and then copy the data from XGCm's like omega h data structure to the PETSc vector. And if you are solving on CPU, you do the similar thing. You just use a for loop to copy the XGC's mesh field to the PETSc's vector, and then call the PETSc to solve the linear equation, basically KSP solve, and then KSP. After you solve, you get the solution. This is normal as everyone knows. Like after solution, we copy the solution vector to XGCm. Similarly, this done like depends on whether you are solving on CPU or GPU. You just directly copy data from GPU memory to XGCm's GPU data storage, omega h data storage, or copy back to XGCm's like CPU memory. So that's basically the process. And when we are solving on GPU right now, we just specify, because we are using DM object, DM-Plex object interface with PETSc, so we just use DM vector type CUDA or DM vector type EIG crucible. So with this one, so like we discussed before, so server partition, we are currently using the same partition as a Polytechnic partition for server partition. Basically, this is the server partition we are using following the Polytechnic partition because it's the easiest and also most important, the big time cost to support different server partitions. So in terms of KSP solve time comparison, like this is a model problem with like different with a 2.4 million like a mesh side triangle, basically triangle on this 2D like 2D mesh. So with different mesh partitions, like we have reduced number of mesh triangles per rack. Basically, you see this is solving time on GPU and this solving time on CPU. Basically, what we saw is like we did not see much difference in terms of using like more GPU or more mesh partition to achieve a reduced time on GPU. So, but on CPU, we did see like a very big reduction corresponding to the more partition used. as of course, even with 12 like mesh partition, still like GPU server may still be a little bit faster compared to CPU. So that's our like observation, and we basically use the CG, and then the Jacobi, like a multi-grid using Jacobi. So this is some like some parameter we used. In terms of code validation, like we have a cyclone base case with circular geometry. So I will not go into the details, but this is basically it's like in each polar plane we have a mesh that is like almost 0.6 million mesh triangles, and then you can see this is just cross mesh showing here, and the case itself is because like we have temperature gradient like basically if this is follow the radial direction along this this polar plane, so with some because of the temperature gradient you have ion temperature gradient turbulence developing, and then for example like here, so you have ion temperature gradient turbulence developing like in the region with like a steepest temperature gradient, then you have turbulence will grow like in the simulation. So we actually just compare the growth rate of our simulation with XGC, basically XGC1 like means XGCs. So we have very good agreement. Despite we are using a distributed mesh, like a distributed unstructured mesh, so distributed mesh basically. So this is just a similar like a different validation case of using a more realistic D3D geometry. People may be familiar with this geometry, and then you can similarly like because like we are in, so we just demonstrate there's a linear growth in the electrostandard potential. This is mean square average in electrostandard potential is a linear growth, and then this one just showing like an electrostandard potential at different time. For example, initially you have like a basic node just because the noise. This one just noise. Then like later time steps like this the turbulence ITG turbulence development. So this is undesirable like effect of the tokamak device. We want to avoid this one. So we want to study how this one actually evolve that then mitigate this undesirable like turbulence phenomenon, because turbulence will disrupt your like a fusion reaction. So with this one, let's talk about the XGCm performance on and basically weak scaling on OFCF Summit computer. So Summit, like everybody knows, like it's right now it's fifth fastest computer in the world. So the weak scaling work we are doing is to each GPU does same amount of work, but evaluate the performance as the number of GPU increase. So basically we use increase the performance side. We use the 256 to 4600 like Summit computer node basically correspond to the 4 with 4600 node we correspond to 4 Summit capacity. So here is the result. Basically, you can see straight line means very good, like very perfect scaling. We have pretty good like scaling when using 256 to 4600 nodes. So this is the breakdown of different components of our simulation. Like particle migration is taking the most time, and then there is like a particle search, also Poisson solver, because here like maybe misleading because this Poisson solver including all the operation related to Poisson solver, not only solving itself but also with like copy data from PETSc to XGCm, copy data back to from XGCm to PETSc, for example. So including everything. So with this one, let's talk about like performance like particle operation GPU kernel time cost, like using the same cyclone base case with circular geometry. So we have basically what we found out like is like for our particle operation for different operation, for example, particle migration, particle search, particle structure review, the push operations, and the charge scan operation. You can see when with fixed number of like amount of particles or amount of particles, use them fixed number of GPUs, using more number of particles per GPU, actually the time cost per particle reduced for most of the particle operation. So which means like this is result on this is result on per month. Somehow did not show this. This is result on summit. This is result on per month. Basically, you can see similar trend. Basically, tells us like we need at least 20-30 million particles per GPU to be efficient on summit computer, or 50 to 80 million particles per GPU on per month computer. So this is corresponding with the memory, different GPUs memory. So with this one, I will just skip some of the presentations. Let's talk about it. Okay. Let's talk about the future work. So future work. So we want to have, there are several things like we can, because we are developing a mesh-centric approach to particle in cell method. So we want to explore the mesh operation. So explore different unstructured mesh and field storage on GPU. So basically, right now we have the mesh field library being developed at RPI. So we use a Kabbalah AOS OA data structure and have better mechanics and performance. So we want to explore how can we use this into our mesh-centric PIC code. And for the particle operation, because particle push like ion and electron have dramatically different mass and speed, so they behave very differently. So how do we explore the performance of different particle discharge on different species? For example, Celsius Sigma and then Kabbalah's AOS or data structure, or even the new one we have DPS data structure being developed here. So another one I think more relevant to PETSc for attending of this conference. So right now we are integrating the latest PETSc version with XGCm is like 3.16.6. So we need to go to 3.19. We only use the CUDA so we want to explore using Kokkos, HIP, and SQL with different hardwares, as what Jun Chao mentioned yesterday in his presentation. So right now we are still in the early stage of properly using PETSc on GPU. So we want to explore best practice using PETSc on different GPU versus on CPUs. With this one, I want to stop my presentation here and take any question you may have. Thank you.
Thank you very much, Chonglin. Do we have any questions? So in the scaling performance that you showed, one of the earlier slides, as you increase the number of partitions, the timing for the GPU stayed relatively flat. It went from 8 to 11 seconds or something like that. And the CPU time started out at around 200 seconds. And yeah, here we go. So is this a performance measurement where we're only looking at the solver, or could you also compare like what percentage of time this is to the push and the scatter and other operations on this?
So here I'm only compare the KSP solve time cost.
Okay, so this is just in isolation. This isn't part of a larger full simulation.
Okay.
Right,
yes. So this is a particle in cell simulation, but in the simulation itself, I only compare the KSP solve like time cost.
Okay.
Yeah. So is there anything like a kind of like strange here? So actually, we were also wondering why there's like no change in the GPU solving time.
Well, algorithmically, it looks like the solver that you're using should be independent of the way that it's partitioned, being a Jacobi-Chebyshev. So it seems like it should be the sort of the same number of iterations at each step. So we must just be looking at something related to the efficiency of those iterations. Interesting thing to explore in the future. But let's thank Chonglin one more time.
All right, thank you.